As I mentioned in an announcement on Learning Suite, I estimate we're about one lecture behind. I'm okay with that. I've built some wiggle room into the schedule, but we're going to begin chapter 2 today after we finish up a couple last concepts. Last time when we ended, we were talking about resonance structures. I haven't said a lot about resonance because I'm assuming that you learned some of that in general chemistry and that you can go back and read the introductory study guide. There's some pretty important stuff in there about how to convert one resonance structure to another that you will see on this upcoming exam. So I encourage you to look at that. In any case, last time we had discussed how this allyl anion has 3 carbons involved in resonance. We discussed how the pi bond can be between carbons 1, 2, and 3, whereas the lone pair can be delocalized on carbons 1 and 3, but never on carbon 2. Remember that in resonance, the atoms are not moving, and actually the electrons aren't either. The electrons are just delocalized in more than one place, which we are okay with because we're used to thinking about electrons now as waves that can pass through nodes and that can be in more than one location. All right, we use this double-headed arrow, by the way, to indicate that 2 structures are resonance structures. That is the only legitimate use of this kind of arrow in organic chemistry. We can use another kind of arrow to convert one resonance structure to another. This arrow is mostly just bookkeeping of electrons. It doesn't necessarily indicate movement of electrons because, as I said, in resonance structures, electrons are not moving. But if I wanted to convert the resonance structure on the left to the one on the right, I would simply start my arrow with the electrons, point to the place where the new bond is going to be. That arrow indicates that the lone pair is going to become a new pi bond between 2 and 3. And then I'm going to move, if I stop there, I'd have too many bonds to carbon 2, breaking the Lewis structure rules. And if all of my resonance structures must be correct Lewis structures, so I have to move the pi bond onto the adjacent atom, carbon 1. Note that these arrows always start with electrons and always point either towards the space between 2 nuclei, as in making a pi bond, or they point towards a nucleus like a carbon or a hydrogen. Anyway, we'll use that notation from time to time. Are you comfortable with what I've described as the resonance hybrid? Are you okay with the idea that you've got one pair of electrons indicated by the dotted line that are delocalized across 1, 2, and 3, and that you have another pair that are delocalized only on 1 and 3, but not on 2? Real quickly, I just want to show you how MO theory gives us a similar picture that corresponds to resonance. And the study guide takes you through this in some detail for background. I'm going to be really clear on what I expect you to be able to do and what I don't expect you to be able to do. When resonance is possible, that's usually there's an orbital phenomenon going on that's called conjugation. And we'll cover this real briefly, though you will learn more about it in 352. The study guide points out that each of these atoms, 1, 2, and 3, are sp2 hybridized, and that each has an unhybridized p atomic orbital on it. In the resonance structure on the left, you could say that those 2 p orbitals are contributing to this pi bond, and the third one would be the lone pair on carbon 3. Over here, you would say the 2 p orbitals on 2 and 3 are contributing to this pi bond, and then a p orbital on carbon 1 is the lone pair. And if that's not making sense to you, you need to go back and look at that MO theory study guide where we talk about it in a lot of detail. Conjugation in MO theory is where we can line up 3 or more p orbitals parallel to each other, side-by-side overlap. So far, most of what we've done has been mixing 2 atomic orbitals together to get 2 new molecular orbitals out. One is a bonding orbital, one is an anti-bonding orbital. But the math of MO theory doesn't constrain you to only look in pairs of 2. You can actually line up more than 2 orbitals together. The major rule is the number of orbitals you mix together is the number of orbitals that you get out. So what I'm going to show you real briefly is what the study guide takes you through, which is, and maybe just on this one resonance structure, I'm going to illustrate the p orbitals I'm talking about. we're looking at a top-down view of this molecule. The circles represent the upper lobes of the p orbitals on carbons 1, 2, and 3 respectively. There's another lobe below that I'm not going to draw just for clarity. Well, okay, fine, why not? And then we'll waste some class time shading things because we like colorful drawings, all right? So this is meant to communicate you have 3 p orbitals that line up side by side. And if you start looking at that, you might be tempted to think, well, where is the pi bond? Is it these two or is it these two? And the answer is yes and no. We need to think a little bit more complicated about it. What I'm going to show you are the answers that come from the MO theory math when I mix 3 atomic p orbitals together. AO is for atomic orbitals, through sort of side-by-side overlap. And I'm going to get out of this 3 new pi type, there's our Pokemon term, molecular orbitals, okay? You don't need to understand the math or the logic for where these orbitals come from. You do need to be able to look at drawings of these orbitals and be able to rank them in energy. So let me show you what they are. The lowest energy combination, which I'm going to call pi 1, we get, and again I'm going to draw sort of a overhead view. I'm just going to draw the framework of sigma bonds that are in the plane of the page. I'm going to drop the pi bonds now for clarity. The first orbital we get is side-by-side overlap of the 3 p orbitals, all with the same wave function sign. I could actually draw this perhaps more clearly or better. An alternative representation would be, nope, that wasn't it. Feel like, well, someday when you are parents of small children, you will be subjected to an endless series of, hey dad or hey mom, watch this, followed by, hold on, that wasn't it. And that process can last, for hours, so just prepare yourselves. Anyway, what I've drawn on the left is a sort of stylistic representation or schematic representation of what this orbital actually looks like. If you want, I can draw the lobes that are underneath the plane of the page. This pi 1 orbital has a node in the plane of the sigma bonds where there's a switch in wave function sign. But what we're really looking at is an extended pi type orbital that extends over atoms 1, 2, and 3. There's one node here, it's in the plane of the page, but there's no other nodes between carbons 1, 2, and 3. So that's our first option, and that comes pretty obviously just from adding together the 3 p orbitals in, with the same wave function sign. I'll draw for you what the highest energy orbital looks like, pi 3. Here again, I'll draw the framework of the sigma bonds, and I'm not going to draw the pi bonds or the lone pairs. Pi 3 we get from side-by-side overlap of the 3 p orbitals, but with opposite wave function signs, such that there are nodes or places where wave function goes to 0. I'm going to highlight those in with a red dotted line. There's a node there and a node there. So pi 3, and actually I could try to draw sort of what pi 3 actually looks like, but it would be just this. So we don't need any other sort of explanation there. So pi 1 has no nodes that are perpendicular to the page. Pi 3 has 2 nodes that are perpendicular to the page. So it makes sense that pi 3 is higher in energy than pi 2, right? That's also why I called it pi 3. So there should be a second or pi orbital. And if we're keeping track of the number of nodes that are perpendicular to the page, I'm going to say 0 nodes here. Just understand all of these orbitals have the same node that's in the plane of the page, so we're not counting that one. We're looking at differences. The one down here has 2 nodes that are perpendicular to the page. So basically for pi 2, the one that's in between these two, I'm looking for 1 node, I guess. Yeah, fine. And it turns out that this one is going to look a little bit strange to you, but it's actually going to explain or agree with something that we've got from resonance structures. One of your study guide says, and again, you don't need to know this, but just as a little bit of background, these orbitals have to agree, these MOs always have to agree with the symmetry features of the molecule. And there's really no way to make an orbital that agrees with the symmetry features of this molecule where carbon 1 equals carbon 2. I'm sorry, where carbon 1 and carbon 3 are identical. You see that from the resonance hybrid. There's no way to put a node here in between atoms 1 and 2 and have that orbital still be symmetric, right? You see that it's offset? And there's also no way to put the node here and still be symmetric. It turns out the only way we can follow the symmetry rule of MO theory is if that single node actually coincides with carbon 2. You don't need to understand that. It's a result that falls out of the math of MO theory. I will draw what this orbital looks like for you. It has 1 lobe on carbon 1 and another lobe on carbon 2. And then, of course, there's the node in the plane of the page, and then lobes below with opposite wave function sign. But this is what the orbital looks like. Note that this pi 2 orbital is only ever on carbon 1 and 3. There's a node at carbon 2. Wave function goes to 0 at carbon 2. All right. So what I would expect you to be able to do if I hadn't identified the number of nodes and if I hadn't given you some clues as to how I'm naming these, I would just draw these 3 pictures and I would ask you to identify, rank them in energy from lowest to highest, and all you have to be able to do there is count, if you can count nodes, okay? So we can rearrange our drawing now in order of energy. If the sort of vertical axis is energy, then we would say, based on what you learned at the beginning of this class, kinetic energy-wise, pi 1 is lowest in energy, then pi 2, then pi 3. At this stage, some people want to ask, well, okay, so fine, you got 3 orbitals, which one's bonding and which one's anti-bonding? There is an answer to that. It's sort of beyond the scope of the class. I'll just take you through it really briefly. The lowest energy one, because we have like sign overlap of wave function on carbons 1 and 2, and then again on 2 and 3, we will call pi 1 a bonding orbital. Pi 3, because we have opposite sign overlap between carbons 1 and 2 with a node in the middle, and between 2 and 3 with a node in the middle, we will call this an anti-bonding orbital. Pi 2 turns out, as your study guide explains, there's no overlap on adjacent atoms, so we'll call this a non-bonding orbital. And it's about the energy of your starting p orbitals that you began with. Okay, those are the relative energies. You understand that? 0, 1, and 2 nodes just ranked that way? Yeah?
So if pi 2 then corresponds to the lone pair.
Yeah, bingo. So if we fill up with the available electrons, notice that from our resonance structure, we have 2 electrons that are involved in resonance, the lone pair and the pi bond, right? So I'm going to fill up these pi orbitals with the electrons that are involved in resonance, 2 in the lowest energy one and 2 in the higher energy one. Now, here's the really cool thing. Maybe I need to rearrange the order. Pi 1 corresponds to those electrons from the resonance structure. See that dotted line that's spread across carbons 1, 2, and 3? That's these electrons in the pi 1 orbital that are spread across carbons 1, 2, and 3. Similarly, pi 2 corresponds to the lone pair that's only ever on carbons 1 and 3, but never on carbon 2. See that correspondence? You may not care. When I first saw that, I was like, whoa, that's cool. But that is why I'm an organic chemistry professor as a job, because I like that kind of thing. All right, so on your practice exam, I'm going to give you a much larger conjugated system. I forget how big it is. I think it's something like this. I'm not going to ask you to draw the pi orbitals. I'll show them to you, but you have to rank them in energy like we've done here. You have to decide how many electrons are involved in this conjugated system with adjacent atoms, all with p orbitals on them. And then you have to decide which one's HOMO and which one's LUMO. Over here, the highest energy electrons, the ones associated with the negative charge and the lone pair, that's pi 2, the HOMO of the system. And if indeed you were to do chemistry with the allyl anion, it would be that orbital that does the attacking. Okay? All right, that's probably too much on that subject, but I wanted you to be able to see that because I feel like that's kind of cool and it sort of illustrates the connection between MO theory and resonance. Now, another question that's come up in some of your recitation sections, you're feeling pretty good about identifying HOMO when it comes to a pi bond or a lone pair. That's pretty easy. Feeling pretty good about identifying a LUMO when it's an empty p orbital or when it's a pi star. Some of you are worried about when the LUMO is the sigma star. And you're right to be worried about that because I haven't given you all the information you need to be able to detect that situation. Our example that we dealt with in previous times that we've met was maybe something like this, a carbon, a CX bond, a carbon iodide bond. And you can look at that and say, okay, I have 3 carbon hydrogen sigma bonding orbitals, I have 3 carbon hydrogen antibonding orbitals, I have 1 carbon iodide sigma bonding orbital, and I have 1 carbon iodide sigma star antibonding orbital. But it wasn't necessarily immediately obvious to you that the carbon iodide sigma bonding orbital should be the lowest energy one. What I told you was that a weak sigma bond will have a low energy sigma star. That's an oversimplification of a lot of things, but it's a principle that will generally work for us. The question is, how do I identify weak sigma bonds? And I told you, you could look it up in the table at the back of your book, or online at the end in the appendix. But it would be nice to develop some intuition to recognize weak sigma bonds. So we're going to actually talk about that. And let's see, weak, weak carbon, and then I need something to abbreviate something general. I'm just going to use Z. Weak carbon Z sigma bonds are associated with very stable Z groups when they're negatively charged and on their own. That doesn't make a lot of sense, so let me show you what I'm talking about. Do you remember last time how we talked about how a nucleophile can attack the empty antibonding orbital associated with the carbon iodide bond? We can attack the carbon iodide sigma star. I've told you before, and you're sort of accepting on faith that that's the LUMO. I explained previously why we attack carbon instead of iodide. If we fill the empty sigma star, the sigma bond breaks. The nucleophile here has attacked to create a new bond between the nucleophile and carbon. And then over here, I minus left, right? There were 3 lone pairs on iodide. Now there are 4, I minus left. we're going to call I minus in this type of reaction, because it left, we're going to be really creative and call it a leaving group. Okay? And some leaving groups are better than others. A good leaving group, LG is for leaving group, is very stable. Let's see, struggling with the penmanship here. Good leaving group is very stable. I don't really believe in anthropomorphizing molecules, but we'll say happy with a negative charge. So weak sigma bonds are associated between bonds between carbon and a good leaving group. All right, that's how you're going to recognize low energy carbon whatever sigma stars. Okay. Well then, how do I know what's a good leaving group? That's why we're going to chapter 2. You're going to think chapter 2 is about acid-base chemistry, and that's how it's written, but it's actually about recognizing good leaving groups. And that's going to be really important for actually the rest of organic chemistry, which is why we put it at the beginning. Okay. In the meantime, as we talk about, as we focus on acid-base chemistry as a way of explaining what makes a good leaving group good, we're going to have the chance to talk about also what makes strong acids strong, and that can be useful too. So, a good leaving group is something, as I said, that is happy with a negative charge. And another way of saying that is saying that good leaving groups are conjugate bases of strong acids. So, let me give you some examples. And what I'm going to show you is basically a table that's present in your text along with some additions from me. Over here in this column, we're going to have the acid, which I'm going to call HA. Here we're going to have the conjugate base. Hopefully that term is familiar to you. If it isn't, you want to read chapter 2 carefully as indicated in the study guide to make sure you understand what that term is. The abbreviations HA and A minus are okay. They're not necessarily great universally. We're going to see that some acids are neutral and have negatively charged conjugate bases, but we will also have positively charged acids that have neutral conjugate bases. So just be a little bit, be prepared to be a little bit general. So the first acid is HI. Its conjugate base is I minus, and this is an excellent leaving group. One way you can judge that, and that we can rank the acid strength or in contrast the stability of the conjugate base, is with this number called pKa. I will tell you a little bit later with maths where pKa comes from. For right now, it is a number that reflects how strong an acid is, and it's a logarithmic scale. The P is kind of like the P in pH. I think it stands for power of 10 or something like that. But in any case, pKa, the lower the number, the stronger the acid. Okay? A pKa for HI of minus 11 tells you that HI is a very strong acid, and accordingly, I minus is an excellent leaving group. Another way of saying, by the way, that that I minus is an excellent leaving group is saying that its electrons are very stabilized. And so you can go down this table of pKa values and see that Br minus is still an excellent leaving group, though it's a little bit less good of a leaving group than I minus. One of the ways, and I'm going to show you this table, And then we're going to talk about the why behind the trends in the pKa table. So right now it's not immediately clear why Br minus is not such a good leaving group as I minus. We're going to get to that. Right now, though, you should focus on using the pKa information to rank leaving groups. Okay? Another way that you should be thinking is strong acids are strong because when they lose their protons, what's left behind, the conjugate base, is really stable. Strong acids have really stable, unreactive conjugate bases. Okay, so we could continue. HCl has a pKa of -7, which tells you that Cl minus isn't quite a good leaving group as Br minus, isn't quite a good leaving group as I minus. So, coming back here, you might make some predictions about reactions. What if I swapped out I for Br minus? Would the reaction be faster or slower? Would it work quite as well? These are some things you can start to think about. We're not totally ready to go there, but we're going to eventually use this information for those purposes. Another one on the list that's pretty important is a positively charged acid that you have seen before. This is hydronium. And it has a pKa of -2. Now I'm going to put an asterisk by this because I want you to memorize that number. The conjugate base of H3O plus is just water, H2O plus. So this is our first case of a positively charged acid that has a neutral conjugate base. Okay? This tells you that actually water is a decent leaving group too. That's going to be important later on when we talk about the chemistry of alcohols. Also, that we're going to include in the same category with hydronium is an alcohol. It's like hydronium, only we've swapped out one of the protons for an R group, some carbon-based group. We're going to call this an oxonium ion, and it also has a pKa of -2. And the conjugate base of an oxonium ion is just an alcohol. And we'll see that alcohols themselves are good leaving groups. Okay. Another acid we could draw is HF. Its conjugate base is F minus. And it has a pKa of about 4. So we just as well deal with this while we're here. What do you notice about the halide acid series, I to Br to Cl to F? Goes down the periodic table, the lowest one is the most acidic. Now, one of the explanations people like to use for why conjugate bases are stable is electronegativity. Because electronegativity reflects how tightly a nucleus is holding on to electrons. And so a more electronegative atom should be, quote, happier with a negative charge based on electronegativity. Well, fluorine is more electronegative than iodide by a ton. So why is it that HF is the weakest acid and that F minus, based on this comparison, F minus there should be a poorer leaving group than I minus? Yeah.
Size.
Is it size? Yeah, I mean, that's actually the only other explanation you can come up with, right? I minus happens to be larger, F minus happens to be smaller. So yes, the large size of iodide allows a little bit more electron delocalization, and remember, spreading out electrons is always stabilizing. And we're going to see this as general, within a column of the periodic table, the size consideration dominates how acidic something is. And the size consideration dominates how stable the conjugate base is. Within a row of the periodic table, you're going to see electronegativity is the best explanation because size doesn't change very much within a row of the periodic table. Okay. Let's see, next on the list we could include, I'm going to fill in some stuff in the middle, but for right now, let's do water. And in the same category, I'm going to put an alcohol. Water and alcohol versus hydronium and the corresponding oxonium ion are a little bit tricky. Water itself, H2O, is a neutral acid that has a negatively charged conjugate base, hydroxide. Whereas the alcohol is a neutral acid that has a negatively charged conjugate base, which we're going to call an alkoxide. That pKa is 16. That's another one I want you to memorize. And now you can see the source of the confusion, which is for some molecules, conjugate bases themselves can lose another proton. You learned about this concept in general chemistry when they talked about polyprotic acids, which you hated, along with the polyatomic ions that you had to memorize. We're not going to be doing a lot of that stuff, but water is an example. Hydronium going to water and then water going to hydroxide is an example of a polyprotic acid, an acid that's got more than one proton that can be removed. So you need to be aware, and the numbers are different, right? For polyprotic acids, the first proton off is always the easiest, and then the second one is more costly. So you need to be aware that positively charged hydronium going to neutral water has a pKa of -2, which is much easier and much more favorable than neutral water going to negatively charged hydroxide. Okay, you need to be aware of that and see that distinction. Also, by the time we get to the pKa range of, if we're sort of here or below, these are all excellent leaving groups. Once we start to get to conjugate acids whose pKa's are greater than 0, we're talking about not so great leaving groups. Okay? All right, let's see. There are some intermediate acids that I want to talk about that sort of come in between water and some of these other, and HF. One is this interesting functional group called a carboxylic acid. Its conjugate base is a carboxylate with a negatively charged oxygen. And its pKa is also around 4. The range 4 to 5 is a decent one for carboxylic acids. Now, some of you may have looked at that and said, hold on, that's just an alcohol. But it's different because of its structure. Alcohols don't have carbon-oxygen double bonds attached to the carbon that's attached to the oxygen. This is a huge difference, right? It's a factor of 1 trillion when it comes to acidity. The carboxylic acid is 1 trillion times more acidic than an alcohol. So how do we rationalize that? And in general, in this class, we're going to rationalize acidity by considering the relative stabilities of the conjugate bases. So, can you think of a reason why the carboxylate is more stable than the alkoxide? Go ahead. It's got 2 oxygens, good. So what should that do? Say that again? Resonate. So you've got the opportunity for resonance. If you relax your eyes a little bit with the carboxylate, you can see similarities between this situation. 3 atoms in a row, pi bond here, lone pair there with negative charge. You can see similarities between the carboxylate and the allyl anion. 3 atoms in a row, pi bond here, negative charge. I mean, don't relax your eyes too much. I don't want you to fall asleep, or we're not looking for one of those magic 3D images. But yes, this is a situation where resonance delocalization allows me to move the electrons from the negatively charged oxygen to form a pi bond between that oxygen and the carbon, and then the other oxygen has the electrons. So resonance allows me to delocalize the negative charge. That's favorable. That is why we're going to call that resonance, I don't know why I put the hyphen there, resonance stabilization or electron delocalization. That is why the carboxylate is so much more stable than the alkoxide, and correspondingly why the carboxylic acid is so much more acidic than the alcohol. Got that? So we're going to rationalize trends in the pKa observations that we have based on things like resonance, or in the case of I versus F, I minus versus F minus, I minus is large, F minus is small. The negative charge on I minus is delocalized and spread out. The negative charge on F minus is localized, and that's going to be the major consideration. Okay? Yes?
So is there a prioritization between like localization, size, and electronegativity?
Let's see, there's various considerations like size, electronegativity, and resonance delocalization. What if multiple of those are in play? Then it's probably not a fair comparison. You just do the experiment and measure the pKa's and see. Yep. For the questions I'll ask you, there's always going to be a very clear comparison. Yeah?
So, let's say that like one conjugate base had like 3 resonance structures instead of like 2.
Yeah.
And you were comparing like one that has 2 resonance structures and one that has 3, and you would ask like, oh, which one is like more acidic?
Okay.
Would you go with the one that has more resonance structures because it would be more stable?
Right. The question is, if you have two acids that are similar, but one has more resonance structures than the other, is it a clear decision? Yeah, the more resonance structures you have, the more acidic it should be. You have to be careful and compare sort of what's changing. So, do I dare to do this? Sure, why not? Here is an alcohol. This alcohol is called phenol. It's got a benzene ring with an OH attached to it. Its pKa is 10. Now I told you alcohols have pKa's of 16. That's true for alkoxides where the negative charge is localized and not stabilized by resonance. But if I draw the negatively charged conjugate base for you, again you have a situation where you have a negative charge adjacent to a pi bond, and that is one where you can draw resonance structures. I could move the negative charge to form a pi bond between oxygen and the carbon of the ring, but then I'd have to break this pi bond and move it onto that carbon to draw this resonance structure, in which I have now delocalized the negative charge into the ring. But you can see that, and that's pretty similar to what we did above with the carboxylate, but unlike the carboxylate, here my negative charge is still adjacent to a different pi bond. And so I won't push the arrows, but I will draw the two other resonance structures that you can draw for this anion, this conjugate base of phenol. And we would conclude that the negative charge can be on oxygen and on these 3 carbons. More places than the carboxylate, but apparently these places aren't enough to overcome the difference in acidity. Why do you think phenol isn't as acidic as the carboxylic acid? Or, in contrast, why do you think the carboxylate is so much more stable than the conjugate base of phenol, which you don't have to know this, but I might say the word, so I'm going to write it down here. It's called phenolate. Why do you think the carboxylate is much more stable than phenolate? Go ahead. Okay, the carboxylate, the negative, in both resonance structures, the negative charge is on oxygen. For the phenolate, in the rest of the resonance structures, the negative charge is on carbon. Why does that matter? Yeah? Right. Carbon is less electronegative than oxygen. So, yes, resonance delocalization is good, but resonance delocalization onto another oxygen must be better than resonance delocalization onto 3 other carbons. And I'm not saying that you could predict that, but you can certainly rationalize it after the fact. Yeah. Okay. Seen some hands, some questions? Sure.
So if the resonance destabilization makes it stronger, why are single molecules at the top? Why do they have higher pKs or lower pKs, I guess, than the resonance structures?
So why do the ones at the top have lower pKs than ones where resonance is an issue? There are multiple considerations when comparing acids. The first consideration is what atom holds the negative charge in the conjugate base. When the atom type is different, then it's hard to see. So I think this is related to a question we got earlier. You could ask me, why is HI so much more acidic than this carboxylic acid? And I'm telling you there's 2 things going on. I minus is a lot bigger than oxygen, but the carboxylic acid is also resonance stabilized. Apparently, the resonance stabilization there doesn't make up for the difference in size that allows the negatively charged, allows the electrons to be delocalized on iodide. So that's an example of what I would call not a fair comparison. And you may be wanting a decision tree that allows you to sort of come up with which is more acidic than this. And we're not actually going to do that. I'm going to give you a pKa table on every exam that's going to have all of the pKa's except for the ones with asterisks. So you're going to be able to tell that something is more acidic than something else. And when I ask you why, it's going to be where there's a clear comparison. So if I asked you why HF is less acidic than HI, you could say it's the size of the conjugate base. If I ask you why is HF so much more acidic than water, how do we think about that comparison? HF versus water, 4 versus 16. Let's see, that's 10 to the 20 times, no, sorry, wrong way. We can do math. 1 trillion times less acidic for water than HF. What's the big difference there? F minus versus OH minus. What's your answer? O and F are from the same row of the periodic table. Size doesn't change very much. F is more electronegative than O. That tells you F minus is more stable than OH minus. Yeah?
So basically, because at the top the iodide is so much bigger than the oxygen, it's able to delocalize a lot better.
That's right. Because I minus is so much bigger than, say, fluoride, it's able to delocalize the electrons better. So within a row of the periodic table, electronegativity is your best bet for comparison. Down a column, size is going to be the major factor. Watch out for resonance. Okay? Let's see. There's a few more that we need to add in this intermediate region. Let's see. And there's more that we'll certainly talk about next time as well. One that's pretty interesting is the sulfur version of an alcohol. So this, instead of being an alcohol, is called a thiol, but it differs from an alcohol only in that we replace the oxygen with the sulfur. Now, I'm going to allow you, well, I've sort of put it. We'll hide the answer by putting it somewhere completely different from where it ought to be. Comparing the thiol with the alcohol and comparing the conjugate base of the thiol, which is called a thiolate, with the alkoxide, we're comparing the stability of the alkoxide with the thiolate. Now, based on what we just talked about, which of those two do you think is more stable? Some of you are saying thiolate. What's the explanation for that? Size. Look, sulfur is down one row from oxygen. Sulfur is bigger. So the same thing that makes I minus more stable than F minus makes sulfur, the thiolate, more stable than the alkoxide, right? S minus more stable than O minus. And indeed, that is what we see. The thiol itself is quite a bit more acidic than the alcohol. The pKa there is 8, so that's a factor of 100 million in acidity that you get from having the negative charge on something that's just a little bit larger. Okay. We need to talk about nitrogen-containing compounds. So what we want to do now are the nitrogen analogs of hydronium and oxonium ions. So here's a nitrogen that has a positive formal charge. This is called an ammonium ion. Okay? This is a positively charged acid, and it has a neutral conjugate base, and the neutral conjugate base is called an amine. And there's multiple varieties of ammonium ions. You can actually swap out 2 or 3 of the hydrogens and still have a proton that's available to be removed. And the corresponding amines look like this. Corresponding conjugate bases look like this. There's some variation, but for the most part, all of these will have a pKa that's around 11. Okay? So compare the ammonium ion, and now we need to adjust our table. I keep having to drag things down. Oh shoot, 10 is less than 11. Shocker. All right, so look at those ammonium ions with a pKa of 11, and then compare them to their oxygen analogs, the hydronium ions, pKa minus 2, factor of 10 trillion. Why is the ammonium ion so much less acidic than the hydronium ion? Look at the conjugate base, nitrogen, lone pair, neutral nitrogen, lone pair on nitrogen versus neutral water, lone pair on oxygen. What's the difference? Electronegativity, straight up, oxygen's more electronegative than nitrogen. The lone pair on oxygen is more stable than a lone pair on nitrogen. Therefore, hydronium is more acidic than the ammonium ion. One thing I want to mention, people get confused, and I'm saying this at the end, so I got to say this again next time. Like hydronium, the ammonium ion has a neutral conjugate base, which in 2 of 3 cases itself has a proton that can be removed. There is a second pKa. There is another Skywalker. Ooh, Star Wars references. First one, write it down, first one this semester. There is another acid-base equilibrium. Some of you are going to get this wrong because you're going to use the wrong number for the wrong situation. I'll show you how that happens next time. But understand that there is a separate equilibrium for going from the neutral amine to the negatively charged conjugate base. Okay, we'll still be on chapter 2 next time. Have a fantastic weekend. And if you're going up to Sundance tonight, watch out for my son.